Greetings, everyone, and welcome to the Complexity Lounge, a meetup where we gather to talk about all things related to complexity and complex adaptive systems. I'm Jocko Selberg, and I co-host the lounge together with Barbara Frontera and Tiani Jones. Today, we welcome Barry O'Reilly back to the Complexity Lounge. Barry is the founder of Black Tulip Technology and a Ph.D. researcher within the field of complexity science and software design. His work focuses on finding new ways for software architects to make decisions in increasingly complex environments. Barry joined us back in 2023, where he talked about residuality theory. Today, he will discuss the philosophical and intellectual journey that he's undertaken and share with us some of the observation he's made along the way. This should be a very interesting conversation indeed. So, Barry, welcome back to the lounge.
Okay, thank you. Go. So let's get started. What you see here in front of you is the cover of my new book, which was released on Thursday last week. And so what happened was last year I released a book called Residues in April. And Barbara reached out to me and said, "Hey, you should come on the Complexity Lounge and do a talk about this." And we emailed back and forth trying to find a date that suited. And it took us so long to find a date and get everything set up that I actually managed to write, edit, and release an entirely new book. And so that's what we're going to talk about tonight. The book is called The Architect's Paradox. And we'll talk a little bit about what that is. But if you see my previous talk on residuality theory, which is the way of building software systems, designing software systems in highly uncertain environments, then this is kind of the philosophical underpinnings of that. And this book has its roots in my PhD work, where you have to write a chapter that says, "This is my philosophical position. This is how I am looking at the world. This is how I view the world around me." And that, of course, sets up the rest of your thesis for how you design your experiment and how you interpret your results and all of those things. And this was a very new world to me, world of philosophy. My background is in pure mathematics, computer science, software engineering. And I got a little bit carried away. And so the kind of overspill, around 200 pages, has turned into this book, which, according to Benjamin in the comments, requires around 125 milliliters of bourbon to get through, which is apparently not a lot. So, so the title of tonight's talk, which has given Barbara feelings, is called The Architect's Paradox: Logic, Uncertainty, and Why There's No Such Thing as a Complex Adaptive System. And I've thrown that little bit on at the end there just to have a little bit of fun in the talk. So I hope no one's got too upset already. But hopefully the ideas that I'm going to show you around that will actually have you nodding, agreeing, and will lead to an interesting conversation. So I run a company called Black Tulip Technology, based here in Stockholm, in Sweden. And I'm best known for a bunch of ideas, collectively known as residuality theory, which is the focus of my PhD, which is in complexity science and software engineering. And before that, I worked at a very big company and was responsible for teaching and leading solutions architects across the globe at that company. My work in the last 10 years involved taking a sort of kind of big step away from the traditional ways of doing things in software engineering in the industry. In our industry, when you have an idea, you write a book and you put a pretty animal on the front, and you go on a tour, and nobody ever questions what you say. Once you're put on a stage, you can say anything. I wanted to do things slightly differently. So I went back to university and I started a PhD, and that's led to the publication of some of these articles that you see before you, some within computer science, but over time taking a slightly more philosophical leaning, which led to this book. Was published in April last year, and it was published as a response to complaints from software developers who found the academic material just way too dense and way too heavy, understandably. So I think. And the second book, which I released on Thursday, is The Architect's Paradox, which is about this kind of philosophical underpinnings, the kind of journey that I've had, trying to understand what it was that I was saying from a different perspective. Because some of these things are things that maybe haven't been expressed before within the industry. You can tell from both of these books that my 11-year-old does the art for them, and so he's incredibly chuffed to have done that and have so many books out there. So what I'm going to do across the next hour or so is to talk about what philosophy is in relation to software architecture, and the journey that I've been through, trying to make sense of this. And what I'm trying to get software architects to do is to think about what their philosophy is. And my thesis is then that software engineering and software architecture needs a bit of a reboot in terms of how we think about the world and how we look at the world. And so the question we're trying to answer at the end of the day is, why are we like this? And using philosophy to question our assumptions, which for software engineers sounds incredibly boring. What are you talking about? Why are we even talking about this? Where's the code samples? And this is a deeply uncomfortable conversation. So where do we come from? What do we believe? How did we come to believe it? And is what we believe true as software engineers? And I'll start off with a quote from this paper that was released in 2016 by Ralph and Tempero, where they interview an enormous number of software engineers. And they ask them, how did you make the decisions in this software structure that you now find yourself working on? How did you arrive at the decisions? If we point at this little bit of the architecture, why is there 3 components? Why not 2? Why not 4? And it turns out that software engineers simply aren't aware of the decisions they're making. And when they're pointed out to them, they have a hard time explaining how they arrived at that decision, why they came to that decision. And a lot of that boils down to reflective practice. And I'm sure most people in this community are familiar with Donald Chance, the reflective practitioner, where we build up the ability to do things, but we're not quite sure how we got it. We're not quite sure what we're doing when we do that. And that leads us to the question around what actually is architecture. This little diagram that I'm showing here is an approximation of how an enterprise architect would describe an organization in general. And at the highest level up here, you'll see that we have these things here. C for capability, where we break an organization down into a number of capabilities. And from those capabilities, then we say that each capability consists of a number of business processes, which we have also defined. And each business process, in turn, consists of a number of software components. And what this does is this gives us a map, a picture, a representation of an organization that looks scarily like a circuit board with lots of little lines running between all of these things. And what I try to get software engineers to understand is that this is not what an organization is like at all. An organization, if we imagine that this little blue character here has a goal, they want to achieve something in the world, and they're surrounded by people and groups of people and technology. And what they do is they stagger around in the dark, making mistakes, getting things wrong. Eventually, at some point, they will reach a market, at which point they have some cash flow, things are good, their business starts to grow. As your business starts to grow, you buy more computers, you get architects. And what the architects do is they rush in and they grab these white arrows and they map the white arrows to precisely this kind of circuit board structure to try and get a grip on the organization. Now, this misses some things, as it's inevitable given the size and the structure and the complexity of an organization, that there are things happening that the enterprise architect doesn't have access to, doesn't see, can't possibly see, the things that are happening in different relationships between stakeholders and external factors the stakeholders may not be aware of themselves. And these things cause tension. And what happens over the course of time is that new technology and new actors appear on the periphery of this network, and all of a sudden there's a new path to reach this market. There's a new way to do the same thing. It comes as a great surprise. And when this happens, this white arrow architecture actually becomes a millstone around the neck of the organization because they're incredibly dependent on it. It's incredibly difficult to change. And it can actually slow the business's ability down to do things. The classic example of this, of course, is that we have Blockbuster, who find their white arrow architecture in their brick and mortar stores and their late fees. They don't see the tensions appearing, the fact that their users hate them. They don't see the new technology emerging on the surface, what the little red guy does. And eventually there's a new way to reach the market. And what you're going to find is that when you try to catch up with the little red guy, Netflix, is that the white arrow architecture, which you've become completely dependent on, is too slow moving, cannot be changed, and it will actually break the organization's ability to respond in its environment. Why does this happen? Why do we believe that this is a good way to do things? Where does the instinct come from? And that's something that we have to ask, because it's not something that's in the literature around enterprise architecture. There's nothing that says this is why we do this. And so the question we want to ask is, what is architecture? What is it in theory? What is it in practice? And to get an idea of this, I like to use this example of a 14-year-old kid called Taylor, whose father was a physics professor. And he took some of his father's textbooks and a little bit of material, and he built a small nuclear reactor in his garage. Which got him into a lot of trouble. It's considered to be a very naughty thing to do. And, since we're leaning into philosophy instead of architecture, one key thing that they do in philosophy is the thought experiment. And so as a first thought experiment, I ask what would have happened if Taylor's father had been an enterprise architect instead of a physics professor? What would he have built in that garage? And the answer is not a great deal. Potentially a small fire if you brought one of those enterprise architect frameworks in, or he may have gone and got some normal teenage hobbies. This discussion highlights the fact that there is a gap between the theory of software architecture and the practice of software architecture. And our theory is a little bit disconnected from reality. And we have to ask, why is that the case? If you talk to a software architect and ask them, well, or if you read any of these frameworks, they'll say, well, what is your work? What is it that you do? And they'll say that they're structured, that they're scientific in the way they do things because they studied computer science. It has science in the name, that it has a mathematical foundation to what they do, which has not been true since the 1960s. They're analytic and they're rational. And if you've worked with software architecture at all, you'll know that none of these things are true. Architecture in practice is sheer, unadulterated panic. We pretend that we're using theories. We definitely do. So if a junior architect comes to you as a practicing architect and says, what should I read? How can I get good at this? We'll give them a list of books. We'll give them a bunch of ideas, but we don't use them. And we don't use them because we've built up some kind of gut feeling that allows us to survive in this world. And the empirical evidence of that is the fact that we can't articulate how we're making our decisions around the structure of software applications. So basically, it's lying. And you don't have to take my word for it. You can go back to 1986 and you'll find this absolutely incredible article by David Parnas, who's one of our kind of most important researchers in the history of software engineering. Parnas writes this article called A Rational Design Process, How and Why to Fake It. And Parnas says that there is no way to produce a rational, repeatable, reliable, systematic design process for software. There's just no way to do it. It's always madness. It's always crazy. It always goes wrong. You always have to reinvent your tooling. You always have to reinvent your process in order to be able to do this. But he goes on to say, there's an immense value in pretending to management that there is a rational, structured way of doing this, and to allow the people around you to think that you're working in a structured way, because it gives you credibility and it gives you some professional respect. This is where we're at as software architects. So, what are some of the problems we have with architecture? Well, the biggest one is something I'm calling the architect's paradox, which is what the book is about. And the idea with this is that the focus on logic that was incredibly necessary in order to get to the computer, in order to get to the invention of the computer, is also the cause of what we call the software crisis. Now, the software crisis is a term that was defined in 1968 at the NATO meetings in Garmisch in Germany. And the software crisis more or less refers to the fact that nothing works, nothing gets delivered on time. And even when it does, it doesn't do what we thought it was going to do. And so this logic that is absolutely necessary in order to be able to invent a computer, in order to be able to program a computer, will get you into trouble if you try to understand the world outside the computer with that particular mindset. Another couple of problems that we have in architecture, the first one and the biggest one, and the reason we have architects and not just programmers, is the problem of time, change, and uncertainty. And so if you look at your standard architectural representations, the standard way that we describe the structure of software applications, you'll find things like UML, Archimate. These are very static pictures. They're frozen in time, and they do not even attempt to represent time in the life cycle of the project, not transactional time. And what happens here is that we all know that an architecture will not look the same in 6 months, will not look the same in a year, will not look the same in 5 years. And the reason it won't look the same over time is because things are going to change. And the reason we kind of avoid this, so the reason we don't even try to deal with this problem, is because we simply don't know what's going to change. And so we sweep this enormous problem under the rug. A third problem is the problem of the unit of software engineering. And we ask the question, what is a software architecture made of? What are its pieces? What are its components at the base level? And to understand what I mean here, we go back to the Greeks. And as we know, Thales, one of the first philosophers, was one of the first to suggest that there was an arche, or a root to everything, something that everything else was made out of. Now, Thales' arche was water. He believed that everything in the universe was made of water. And that is, from our perspective today, very obviously wrong. But it's not his conclusion that's important. The thing that's important is Thales' instinct to ask, what is at the base? What is at the root? If we reduce everything down, what do we get to? And not very long after Thales, who was working 2.5 millennia ago, another philosopher called Democritus came up with the idea that everything was made up of tiny little things called atoms. And that idea has stuck with us over the course of those 2,500 years. And so physicists have the atom, chemists have the molecule, biologists have the cell, glossing over a lot of things, obviously. But this is an incredibly powerful idea in Western thinking, that once we have a grasp on some kind of arche, some kind of foundation, we can begin to build a set of paradigms and ideas around that arche, and we can start to move forward in terms of scientific knowledge. This is an incredibly important step in the development of Western thinking. Software, however, has been on a bit of a journey, and we haven't really grasped this yet. We keep moving and we keep changing constantly. And we're still very much in our Greek phase of bumbling about and asking if it's earth, fire, wind, or water. And we've moved from machines to punch cards to procedures to modules to objects. And we get to objects, then we lose our minds for a decade and a half. Then we finally get to the service. Things start to work a little bit better. But every year, there are new ideas around this. There are new RK that are being produced. And when you have a different RK, a different way of looking at the world, a different unit, it drastically informs how you look at the world. And we'll look at that a little bit later, a little bit more later on. One of the things that happened after the Garmisch conferences, everyone got together, 1968, said, why are we so bad at this? Why is this so incredibly difficult to get software right? Why does it cost so much? Why doesn't it work like proper engineers work? They come along, they gather some requirements, they write a specification, they build something to the specification, it works and they get paid and everyone's happy. Why do we keep screwing this up? And the solution to this problem was for us as software engineers to become more like proper engineers and actually deliver our jobs, to deliver our work in a reasonably structured way that worked. And this led to something which I call the engineering paradigm, where software would then spend several decades trying to pretend that it was an engineering discipline and that we would work in the same way as other engineers and be able to deliver with the same level of quality and the same level of certainty. And certainty is what these guys were out after. And this engineering paradigm really is a paradigm. It's affected everything that we've done since '68. We're constantly trying to see ourselves as engineers, and I believe that we are on the verge of that paradigm breaking. And Thomas Kuhn, in this book, which I'm sure you're all familiar with, The Structure of Scientific Revolutions, talks about how paradigms will shift over time. And the sign that they're going to shift is the stacking up of anomalies and patches on top of the theory. And we've had some fairly significant anomalies, which is the entire history of our industry, showing that this idea is just simply is working. And I think the biggest attack on the ideas of the engineering paradigm was the agile movement, which was 25 years ago now, 24 years ago. And we are due a shift in the way that we think about this. So these problems that I'm talking about, what's the base unit of software? How do we deal with this constant shifting RK? How do we represent time, change, and uncertainty? These are philosophical problems. And very often what I discovered, I would find that some developers or engineers are at loggerheads arguing over things, and what you'll find when you scrape at the surface is that they're philosophically opposed to each other, but they've never been taught how to express things in that way. And in order to get them to understand this, what I've been trying to do is to give them a little introduction to philosophy. And one of the key things that I try to get them to understand is this idea of the philosophies of stillness. And the architect's paradox is caused by an impulse, and that impulse is to reach out to this world that is moving from a position where we're working with logic, we're working with chips, we're in complete control of what we do. We tell the machine what to do, it will do exactly what we tell it. And then we've got to reach out into this world of people and organizations and markets and businesses, and we reach out into that world with no other tools than the logic that we've been taught at university, that way of looking at the world. And what we do is we try to hold it still. Even though it's moving, it would be much better for us to hold it still. And we have to hold it still because we have to map whatever conceptual picture we build of that world to software structure, which is always going to be still. And this is not a new thing. This is not something that's entirely based on software engineering. This is not our thing. We like to think we are on the cutting edge. We are the first people to have ever done this. This has been going on since ancient Greece. A really good example of this tendency comes from an article that was written by a guy called Edgar Dijkstra in 1974. This guy's fundamental to the history of computer science. And he wrote an article in 1974 called On Scientific Thought, where he said that the people who worked with software engineering were deeply unscientific, and that when we brought in real scientists into software engineering, they very quickly lost contact with their scientific training and started just trying to chip away and hack and solve problems. And his solution to this is something he calls the separation of concerns, which is a phrase that becomes incredibly famous within software engineering. But very few people have actually read this paper. They will use the phrase repeatedly across the industry. And the idea is that you focus on one thing at a time. You take one thing at a time and you focus on it. And while you're focusing on that one thing at a time, everything else is still. And so this urge to hold the world still is a way for us to be able to access the world using the kind of training we've had in logic. Now, if we go a little bit further back than Dijkstra to the pre-Socratic philosophers, there is a difference in looking at the world that we need to be aware of. And one of those things is the difference in the way that Heraclitus and Parmenides look at the world. Parmenides is this guy here. You can see he's dressed in fine robes. He has a project plan in his hand here. So very obviously a project manager, program manager, something like that. And Parmenides says that the world is one and the world is still, and that everything that we see as moving and changing is an illusion caused by our tiny, feeble brains not being able to absorb the world around us. And his counterpart then in this way of looking at the world is Heraclitus, which is this guy here, who looks like very much like a senior software engineer. And Heraclitus says that no, everything is moving, everything is changing, everything is constantly on the move, including us and everything that we're trying to observe. And he's famous, of course, for the phrase that no man steps in the same river twice, because he's not the same man, it's not the same river. Heraclitus thinks that everything is on fire, everything's made of fire. So very obviously one of us, a software engineer. And these two present very, very different ways of looking at the world. And Plato is going to side with Parmenides as he moves philosophy forward with the next generations of philosophers, and says that the world is actually still and unchanging, and it's our sense experience that gives us the illusion that things are moving and are changing. And so this will have dramatic effects on Western philosophy and dramatic effects on software engineering. It's the start of the kind of thinking that's going to make it possible for us to actually deliver computing. So when you ask the question of a software architect, what is your philosophy? You probably aren't going to get a particularly sensible answer. And that's because as software architects in our traditional training, unless you take up philosophy as a hobby, you won't have an answer to this question. You won't ever have been trained to answer this question, and you probably won't have any strong opinions about it. You might say something about Agile, you might say something about Java, you might say something about service interfaces, but it's not really a philosophy. The default philosophy of software architecture is something that you will find very, very quickly start scratching at the surface. You will find this in the ideas of the vast majority of software engineers. They tend to have a default philosophy in different degrees, but not be particularly aware of it. And so the question we ask is, where did we come from? Where did we get our ideas from? And if you think about software engineers, this is where we came from. This group of thinkers here, who all have one common thread running through their thought, and that thread is one of positivism, more specifically logical positivism. And two of the most important figures here, von Neumann and Turing, had very close relationships with this trio here, Frege, Russell, and Wittgenstein. Logical positivists, people who put logic at front and center in their understanding of the world. And this has leaked into computer science. It was necessary that these thinkers existed in order to get to computer science, but it persists in the way that we look at the world as computer scientists today. And so their way of looking at the world is one of positivism, which obviously has its roots in Comte, who believe that, yes, we live in this clockwork universe, that there are laws that govern how the universe works, that we can reduce the universe down to a number of mechanistic constructs, and that this can also be applied to social systems, most importantly. And when you look at how the software engineer interacts with the world, they design things as circuit boards, as chips. This belief in an objective, structured, ordered universe is pervasive. It comes from our computer science professors, who are the children of von Neumann and Turing, who are, of course, deeply related to Frege, Russell, and Wittgenstein. And so this chain of thought, this way of thinking, gives us computers, but it also gives us the software crisis. There is more than one way to look at the world. And if we want to look outside positivism, juxtapose it with something, a good candidate for that, something called interpretivism, which comes from the social sciences. And so positivism seeks laws that govern the universe, believes that you can use the scientific method to investigate social systems. It's based on observation, experiment, logic, empiricism. It believes that knowledge is out there and that it's discovered. And this, if you ask software engineers, this is what they generally believe in. This is the view of the world that they've inherited from their professors, from their surroundings, from our industry. And I would have been the same a few years ago. Interpretivism allows different views of the same reality. It rejects the scientific method for social systems, and it believes that knowledge is transmitted. It's not discovered, but it's transmitted through ideas and debate. And this causes a bit of a schism, because even though the software engineer will believe in everything in the positivism column, the way they learn and the way they navigate the world is very much in the interpretivism thing. So that causes a little bit of confusion. If you scrape a little bit harder, what you'll find is the default philosophy of architecture, and it consists of a number of things. And the first thing you'll find when you talk to a software engineer is a belief in something called essentialism. Essentialism is an idea that comes from Plato and later from Aristotle and a few other thinkers, but it's the belief in essences. It's the belief that everything has a something that makes it it. And the search for these essences becomes an intellectual exercise in which some people believe is the path to wisdom, especially Plato. And Plato had this belief that we exist in that we live in a universe where these forms, these essential forms of things, are real. And in some heavenly realm somewhere, there is a perfect form of beauty or justice or a cat. So somewhere there is a perfect cat, and every other cat on earth is just a crappy copy of that cat running around. And when you tell this to software engineers, they will laugh and they say, "What a strange idea!" And these Greeks, they knew nothing. They were very strange ideas about the world. And then you ask them about object-oriented programming, in which we have a class description, which is a perfect object that lives in a heavenly realm, and all of these crappy little copies of instances which can partake in other objects like beauty and justice and all of these things. Object orientation is a pure interpretation of Plato's ideal forms. And you'll find these ideas echoed in things like Togath's architectural building blocks or solution building blocks as well. So this belief that there is an essence is something that you will find in almost every software engineer. The second thing that you'll find is a belief in some form of structuralism or structural determinism. If you go back to the 1930s and look at Saussage's ideas, you'll find this idea that there is a structure underlying our language, and that structure is the key to understanding what's happening in reality. And you'll see people like Levi Strauss, anthropologists, take this idea to say that the same structures in social systems can help us to understand how they actually work, that there's a source of truth behind this. Linguistically, you'll find these ideas echoed in the practice of requirements engineering, where we're taught and trained to make our statements atomic, to make sure that they're logically sound. to uncover the structure between them. And even things like domain-driven design will attempt to hold language still. And the belief is that these complex systems that seem to be beyond the computer can be governed by mapping the relationships between language, between predicates, between structure. You'll find these ideas also echoed in the work, especially in the work of Frege and Russell, and even Wittgenstein. And this, once you start to try and understand something very big with a lot of moving parts, essentialism starts to become difficult. And so we start to look to the structure of the system. Causality, mechanism, and determinism are things where we tend to see social systems as machines. And in machines, of course, there is efficient causality, and we get this idea that the entire world beyond machines is mechanistic, even social systems, and mechanistic, therefore deterministic, and we can predict what's going to happen. And this thinking has its roots in Descartes and Newton, and it pervades the thinking of software architects. In real life architecture, stuff keeps happening. We have no idea why, but we still lean back on this philosophical foundation because we simply don't have anything else. And PowerPoint seems to have crashed on me. I wonder if my connection is gone. Can you still hear me?
We can.
Yep. Okay. Let me just try and fix PowerPoint.
I can still see your slide.
Yeah, yes, it just wouldn't change. So the fourth thing you'll find when you scrape at the surface of how an architect actually thinks is a naive idea of cybernetics, a very naive interpretation of organizations as machines, organizations as feedback loops, organizations as control systems. And you'll find those ideas from Wiener, where we tend to see organizations as simple cause and effect things. We talk about organizations as thermostats, more or less, and you'll find that in there as well. All of this surfaces through the architect's obsession with models. Architecture is all about models, machine thinking projected onto our reality. Of course, this has its roots in Newton's corpuscles, in his model of the world that isn't quite the world, but it still works as a model. And there's a lot of these models. All of these ideas can be combined into a singular way of thinking, which I've chosen to call logical structuralism. It's not quite structuralism. It's not quite Russell's logicism or Frege's logicism, but it's an attempt to logically structure the world around us using a hodgepodge of these ideas. It's never been really formally stated. It's very much an accidental philosophy, a default philosophical position that arises in software architecture and software developers. And it's very much a philosophy of stillness and a substance philosophy. It's very much focused on the things around us, how we describe them, how we understand their relationships to each other. And it has its roots, of course, in reductionism, which is, something we want to avoid, especially here in this community. And what logical structuralism then tends to do is it takes reality and it covers it up with the models that we as software architects produce, and it then forces us into a position in order to pretend like we're engineers, to ignore the reality behind these models and interact only with the models that have been produced. And this causes us to lose touch with reality, which leads to the very old and not entirely wrong accusation that us architects have to face all the time, of being ivory tower architects. A philosopher that's interesting from this perspective is Baudrillard, and Baudrillard has written this book called Simulacra and Simulation, which many of you might have read. It's a very famous book, made even more famous by featuring in the movie The Matrix. You can see a still from The Matrix here, because this is where Neo keeps all his contraband in his hollowed out book. It's actually a copy of Simulacra and Simulation. And in this book, Baudrillard talks about how we live our lives through a a simulation through a model of reality instead of interacting with reality itself. And this is, he quotes Borges, and this goes back to the idea that the map is not the territory, which means that as architects, we're not actually stuck in an ivory tower. We are trapped in the matrix, which is a matrix of our own making, interacting with something that isn't real. Whenever you tell software people that you're in the matrix, they immediately think, well, that's pretty cool. I must be Neo, I must be Trinity. But they're not. They are the architect. And the architect in the movie actually looks a little bit like Norbert Wiener. And according to the sources I've read, that is not an accident. This idea that people and society are machines is very much in his view of the world. You can tell that he's an architect because he promises utopia in version 1.0. He continually fails to deliver that. Instead of changing his mind, though, he just builds new mechanisms and patches to capture that failure. So he builds the Oracle, he builds Neo, he builds the Agent Smith, building patches to fix the patches to fix the patches. And eventually he gets caught out by one of those green arrows, which he doesn't see coming, which is the impact that love is going to have on Neo. And that brings the whole thing tumbling down because there were things in the model that he just couldn't see. And he expects things to unfold as they did in the past. And so he very much is an architect. And so the question is, how do I escape this matrix? How do we get out of this? What essentially is happening is that our essences, which we form, our customer object, our order object, our data structures, these things start to get out of step with the real world around them. And when they get out of step constantly, all the time, we generally use the word complexity to refer to this situation. Now, as we move through time in Western philosophy, there is an attempts to reject this Platonic way of thinking. And most of them have their roots then in Kierkegaard and then Nietzsche, who start to push back against this Platonic way of thinking. And what we eventually get then is the existentialist movement, where there's a rejection of logic as the essence of thought, and a search for meaning in how we live, and a challenge against these philosophies of stillness, where people are saying, sometimes quite histrionically, that this isn't the way to live, that logic is not the way to understand the world. Nietzsche will say that the focus on the Apollonian destroys who we are. The focus on science above poetry is dangerous for us. And they start to challenge the philosophies of stillness, and there's a lot of howling and screaming, and it's very like the Agile movement, the existentialist movement, and there's this challenge to the philosophies of stillness. And Agile was essentially software engineers on the coalface getting tired of these attempts to hold the world still because it just wasn't working. And for many people, then Agile becomes about identity, about finding meaning in your work, about finding your own way of doing things, about expressing your own individuality in your work as a coder. And there's a whole lot of Nietzsche and Sartre in there, if you look at it through that angle. And the question then is, what do we do? Well, what we're experiencing now is complexity. How do we deal with complexity in software? Well, the first way we try to do it is to suppress complexity. Firstly, by saying you ain't going to need it. That's never going to happen. Let's just build what's in front of us right now. Secondly, by saying, look, we can encapsulate these things behind component boundaries. None of that really works. Some believe that the way out of complexity is just iteration. An iteration will keep you busy, but it's not guaranteed to get you out of this trap if your essences and appearances aren't matching up. Some believe that the way out of it is experiment, an empiricist approach where we design and test hypotheses. But I don't think that that's a particularly revolutionary idea, but it's a clever way to talk about it. The way out of complexity has always been a new set of concepts, a new philosophy, a new way of looking at things. And so Newton's way out of complexity, for example, was to have an apple fall on his head and make a massive jump. So PowerPoint is doing that thing again. Let's try and see what we can do. Okay. And so this brings us and brought me to the complexity sciences, of which I don't need to tell any of you this, a scientific discipline that works with flux. It can be a study of everything we don't understand. There's a philosophical description of the problem of complexity, which I think is really good. And this comes from a 1925 book by a Cambridge philosopher called C.D. Broad, called The Mind and Its Place in Nature. And this talks about the concept of emergentism. And this is an idea that I'm using to get software engineers to understand what is actually happening around them. So when we look at something and we try to understand its structure, then we look at it like this little bunch of dots here, and we say, well, this is the thing we're looking at. This is the organization. This is the thing. It's a bunch of stuff. It's connected to other stuff. We can call it a system. And the way we study this is to break it down into little pieces using these philosophies of stillness and get a grasp on what this thing actually is. But what happens is that something emerges, something that isn't there in these little pieces, something that wasn't there before. And the obvious example here is consciousness. And so all of these little things, you can think they're neurons. You put all of these neurons together and pack them very tightly, very densely. And all of a sudden, you have this cloudy thing here that appears, and that thing is called Barry. And Barry has ideas about things. And if you take these little cells and you chop them all up and you look at them under a microscope, you won't find any of Barry in there. And Barry then can start to do things that are going to push back on this system. So, for example, Barry can start to eat a lot of sugary food and drink a lot of beer, and that has an effect on these little things. It causes them to perform much more badly, which makes Barry depressed and causes Barry to drink more beer, eat more sugary food, and this starts a cycle of constant movement. And this cycle of constant movement is known as supervenience. And this is what happens whenever we have these emergent systems. This is, of course, called strong emergence. It's pushing back on the system, which influences what emerges, which influences the system. And this causes constant movement. This is a problem that has been talked about, described across the millennia by different philosophers. Spinoza here has his way of talking about it, natura naturans, naturata. Nietzsche talks about the Apollonian and the Dionysian. Descartes calls it the body and the mind. And Broad calls it the mechanical and the emergent. And this idea then challenges us to look to a new way of thinking about these things, and I call this the philosophies of movement. And this is where software engineers can begin to take inspiration, begin to rebuild their own philosophy, their way of looking at the world. And two important philosophers for me in this journey are Bergson and Deleuze. Both of whom can easily be described as process philosophers, that is, as opposed to substance philosophers who believe in things, in material things. They believe in process, which is constant movement. Things are constantly changing. And the line that I love from Bergson that helps us understand what's actually happening here, that gets this message across to software engineers, is that when we try to logically analyze and hold something still, we lose its meaning, which is what I meant when I was talking about Baudrillard as well. And Bergson says that when you focus on the notes, you can never hear the tune. And for us as software engineers, we have stakeholders who are singing very many different tunes, and we tend to never hear those tunes because we focus entirely on the notes. And the question here is, how do we gain knowledge? Do we gain knowledge by chopping things up, by understanding all of the details, by putting logic at the center, which is the natural instinct of the software engineer, which they will naturally tend towards? And is this the right way for us to learn? And Deleuze and Bergson say no. The way that we learn is more like this. Whenever I move to a new house and I decide on the first day in my new house that I want to go for a walk, then I can go into Apple Maps and I can pull up this map, I can create this map, and I can decide I'm going to go for this walk. Now, this walk that we have in front of us here from Apple Maps is an abstraction. And it is an essence, okay? Because every walk everywhere in the world that Apple has mapped will look like this, the blue line going around, hopefully coming back home again. And so it represents a form of knowledge, but it's a pretty useless form of knowledge. And the way that Bergson and Deleuze describe how we come to knowledge is like this. We go for a walk. And the first time I go for a walk, around this walk, I'm looking at my phone. I'm really focused on the details. I'm focused on getting this right, doing this correctly. And I walk around this walk, and my concern is not to get lost. Now, the second time I take this walk, I don't have my phone with me. I know the way. I don't need to stress as much. But I notice a difference. This is really important to Deleuze. I notice that there's something different about this walk. There's something different this time. And I notice that this path is shaded. And in Sweden, where I live, a shaded path in the summer means mosquitoes. And that means that I'm not going to take that path on this day. This is knowledge. On another day, I realized that the paths here down by the water in the winter are not sanded, they're not gridded, no one takes care of them in the winter. They're incredibly dangerous, and you should avoid them in the winter or you'll get a very, very cold bath. Not something they advertise to foreigners like me when we move here, but something that you find out pretty quickly. I realized that if I take a walk in the summer, things are slightly different again. I notice new things about this walk. I notice that if I leave at a certain time, I get to see this kind of sunset. And I also realized that on certain days of the year, I just shouldn't leave the house at all. And what happens is that over very many walks, I walk around the problem over and over again. And as I repeat that walk and add it to my memory, all these tiny little differences add up to knowledge of this particular walk. And it gets to the point where if you want to take this particular walk that I'm showing here, then you will see that I am a much better source of knowledge than Apple Maps. And this concept, this idea, is described in one of my favorite works of philosophy, Difference and Repetition, by Gilles Deleuze, was written in 1968. And it describes this way of building knowledge. This is how we come to know the world. If you're a software architect, there's some very peculiar things about the way that we do our jobs. We all believe in different tools, for example. But none of us can show that the tool that we use, the framework that we use, is actually the thing that contributes to the success of our projects. And if you take any particular architectural tool and ask the question, how many successful architectural projects in the world have used this particular tool, then what you'll find is that the answer usually is less than 5%, because everyone uses different tools to achieve different things. And then you ask the question, well, is that tool therefore necessary for a successful architecture? And the answer has to be no. And this can be extended ad absurdum to the point that no architectural tools are actually necessary for a successful architecture. And the truth, when you look at knowledge building from this perspective, is that architecture is not architectural success is not a function of the tool that you use, but a function of the number of walks. And the architectural tools that we use, be it requirements engineering, risk management, capability mapping, any of these things, process mapping, all of that stuff that we do, is actually just a way of forcing the architecture to take a walk around a problem, and take a walk around a problem from a slightly different perspective so that you'll notice differences. And it's these differences that build up our knowledge of the thing instead of seeking the essence. The essence gives you this, the differences give you this. And that is the level of knowledge we need in order to be able to build architecture and make conceptual models and solve problems as architects. And so this is an incredibly powerful theory of architecture that helps us understand and get away from all of these asinine arguments about which tool or framework is better or a better place to solve this problem or solve that problem. My work as a consultant involves rescuing crashed projects. And I can say that every crash project that I've ever seen has been a result not of the choice of wrong tools, not of the choice of wrong components, but as taking too few walks around the problem. And successful architects over their careers learn how to add enough walks so that they have enough perspectives before they build that crucial model, that conceptual model that eventually becomes the software structure. Another thing that's important is the concept of criticality. Criticality is the ability to withstand things that aren't in the spec. And a lot of my work, if you've seen my earlier work, is about how to get software architectures to survive off spec. Criticality, then human systems, social systems, forests are critical systems. For programmers whose focus is on logic at university, the goal is always one of correctness. For architects, the goal is criticality. And these are two completely different things. And it means if you're a programmer and you're very good at bringing correctness to the code that you write, learning how to bring criticality to the overall solution as an architect is a completely different skill. The two things are very, very related, but they are completely different skills. What this gives us is a set of new concepts, a very, very different way of thinking about how we're going to navigate this complexity. And what we're saying is that we want a process view of the world instead of substance, criticality instead of correctness, difference instead of essence. And this is a huge, huge philosophical shift, especially for software engineers who find all of these words a little bit scary. My first book, which was released in April, it's called Residues, Time, Change, and Uncertainty in Software Architecture, describes a new unit of architecture. And that unit captures time, change, and uncertainty, and it allows us to design architectures for many different trouser legs that gives us, at the end, an empirically producible result that, which I talked about here last time, I guess you already know this, which shows you how we can build architectures and prove that they have a better chance, a better degree of criticality, a better chance of surviving off spec. And a lot of these ideas were arrived at by going way underneath the code and all of that stuff and thinking about things in terms of philosophical discussions, which brings us to the discussion of why there's no such thing as a complex adaptive system. And this is kind of a little add-on I've done to this talk to make it more entertaining for you all here tonight. So one of the things that comes out in my new book is this choice to focus on attractors rather than universals. And a universal is a property of something that applies in the general case. It's like an idea, a generalization, one of Plato's forms. For example, whiteness is a universal. And you can say that, are all the things in the world that are white sharing the same kind of whiteness? Is it the same thing? And so you can ask the question then, is the whiteness of the polar bear the same as the whiteness of a snowflake? And Plato would have said yes, as would Aristotle. Residuality focuses instead on the idea of an attractor, that a system arrives in a certain position, that the polar bear and the snowflake have arrived at whiteness, they have become white, and it's not necessarily the same white. The attractor is local, it's not universal. Russell, who started this ball rolling, believed that universals actually existed in the world. And that they were central to our language, central to our logic and our understanding of reality. And we also believe this too, far too often. There's no scientific evidence for their existence. It's a metaphysical existence. It's a speculation. It's a nice, easy intellectual shortcut, but it does have some serious consequences. And the serious consequences can be revealed in asking this simple question: is the security of a photo sharing app the same as the security of an app running in a nuclear power station? Your immediate answer to that will be no, it absolutely is not. But our entire industry treats security as a universal, something that's applicable across all systems. Now we can extend this argument one step further and ask, what is agility? Is the agility of the cat the agility the same as the agility of the software team, your immediate instinct would be to say, no, it's not. It's a different kind of agility. But if you've got two software teams and they're both experiencing agile software delivery, is that the same agility from one software team to the other? Now that I've made you think about the difference between the cat and the software team, you're going to start to think, no, maybe they're not. Maybe it's wrong to think that there's a universal thing called agility that exists across software teams. Agility is an attractor. It emerges in teams, and it isn't the same agility in every case. There's far too many variables to know what causes agility. Now, when you work in an agile team, you feel it. You feel that ability to respond to change. You feel that willingness to meet the challenges that are turning up. It feels absolutely amazing to work in an agile team, and it's perfectly understandable that everyone wants to work in an agile team. And whenever we approach this way of looking at things, the first thing we try to do is find the essence of agile. What is it that all these teams who are experiencing this agility, what do they have in common? And the guys who wrote the Agile Manifesto got together and said, what's the essence of what we all call agile? Because we've all experienced it. And they'll say, well, it's focus on, it's a focus on delivery over process, and people over tools, and all of these things. And this is the logical structuralism kicking straight back in and saying, this thing is happening, it must be the same everywhere. Let's try to get to the essence and then to the structure, and then we can map it, and then we can control it. And that is logical structuralism in action. And so agility is something that we've all felt, most of us in our careers, as engineers, as architects, as whatever role we have. And it feels incredible when it happens. But it's not an essence. It's not something that can be recreated over and over and over again. As Parnas said, though, maybe there's some value in pretending that we do. And maybe we should lie about it. It's not the same agility. There's no framework, no formula, no relationship between cause and effect. If you get agility to emerge in a team, that's fantastic. But if you move that team to another organization, to another country, to another business, if you change one person out of that team, the bubble might burst, the attractor might shift, and you may not know how to get it back. So agility is an attractor, not a real thing. But it's not just agility. Almost all of the ilities in software engineering, and these are the things that an architect has to be responsible for and has to take responsibility for. Flexibility, maintainability, security, performance, usability, extendability. I've said all the cool ones now. Scalability, availability, all of these things are all treated as universals, and they can be treated in the same way. And there's a whole range of companies who want you to believe that these ilities are universals, because then they can sell you their universal solution or their universal framework for solving this. These things are all emergent. They are all affected by each other, and they all need to be very carefully managed. Now, the industry, as it works today, takes one of these things at a time and fetishizes it in order to sell us frameworks. And so we've got security happening right now. AI ethics is coming. Resilience and reliability are currently things that are fetishized by the industry rather than being looked at as attractors. They are local attractors, a function of the context. They're not universals that apply everywhere. Just because I've managed to build a resilient application in one branch, in one particular market, at one particular time space, doesn't mean that I'm going to be able to redo that in a different business, in a different market, in a different country. The odds of me being able to do it are maybe a little bit higher, but if you try to replicate exactly the same thing, as a lot of people are finding out with agile frameworks, it just doesn't work, and no one really knows why. And this requires careful design rather than repeated processes. And so we get to the big one, the teaser that I put in the abstract to make you all come here tonight: complexity. And exactly the same argument is going to be used for complexity. Is the complexity of the anthill the same as the complexity of the organization? Absolutely is not. We are not ants. And complexity is emergence. It's the presence of something that can't be analyzed or reduced. And this is a phenomenological essence again. It's experienced the same way. That doesn't mean there's a universal complexity. For example, one of the huge problems that you'll find if you're working with software people is that you'll constantly explain to them that software in itself, a software application, is never complex because it's mechanistic, because it's understood, because it's determined, because it can be traced, it can be mapped. But if you take a software engineer and put them into a new code base, which they've never met before, what they experience, what they feel, will be no different than the complexity of emerging in a real life, in a real materially complex system. So there's no universal that is complexity. Complexity is an attractor, just like agility, just like security, just like all of these other things. Adaptation, then, adaptation is the ability of a system to respond to new challenges that it hasn't met before. The ability to adapt to a particular challenge is an attractor. It doesn't always happen. Sometimes the system just dies. Sometimes it doesn't adapt. Sometimes it just hobbles on. The mechanisms and the actors involved in that adaptation are always different. There isn't one mechanism called adaptation, even inside the same system. A system will not adapt to one particular challenge in the same way that it adapts to another particular challenge, and adaptation is never guaranteed. So system A adapting to challenge B is definitely not the same as system C adapting to system C or system D. So they have nothing in common. So the word adaptive is not a universal either. Adaptivity is not a universal. It is a local attractor, not a universal thing. And the word system, if we're going to go for all three, for Bert and Alfie, the system is a universal. There should be, or there could be, a way to uncover how systems work at a higher level. That the system is something, if we understand one of them, we'll be able to work with all of them. System is not a universal. And so, since there's no universal for complexity, adaptivity, or systemicity, I guess would be the right word, then it is by extension nonsensical to talk about a complex adaptive system beyond individual instances. Complex adaptive systems are local attractors in a context, not universals. And what I'm actually saying here, this position philosophically would probably be described as nominalism. I'm saying that the complex adaptive system is just words. It's nothing. It's not something that's actually real. So when I say there's no such thing as a complex adaptive system, I'm saying the words exist. You can use them to describe something, and if that helps you communicate with someone else, that's fine. But this is an anti-essentialist position. We're saying that there is no essential form, there is no essential complexity in which all complex systems take part. They are all different. And the way to address those complex systems is to talk about attractors rather than universals. This stops us from becoming beholden to frameworks. SAFE, TOGAF, all of this stuff that we all complain about, all of this stuff is attractors that we're doing. All of this stuff comes from the need to find essences to make things simple. We want to encourage our people to think anew every single time, and not to think that there's a particular reaction that you have to have every time you feel this thing that we call complexity, that we put the word complexity onto, because it's never the same thing. The river is never the same. And this is something that I think is incredibly important. What actually happens in the software industry, and this is something that causes me a great deal of frustration because I've spent 12 years of my life in the complexity sciences, is that when you bring the ideas of the complexity sciences into software engineering, they get sucked up by this thing that I call logical structuralism, and they become disabled by it. They become corrupted by it, and they become, at the end of the day, a part of it. And if you combine logical structuralism, which I've described here as the sort of default philosophy of a software architecture, with the complex adaptive system universal, the idea that a complex adaptive system is this thing that appears everywhere, then you get more of the same. And if you read on Ralph Stacey's Dominant Discourse, he foretells this, where he talks about how The MBA way of looking at the world eventually pulls the ideas of systems thinking into this dominant discourse and just brings them back to more of the same thing. And so the idea, the universal of the complex adaptive system, can very easily be pulled by this logical structuralism, which a lot of people have a lot of stuff, a lot of their worth invested in, to pull CAS back into becoming a philosophy of stillness. And this is one of the dangers I see with the ideas of complexity in the software engineering and software engineering, or the software industry, or in tech. These ideas are pulled back into it, and you'll see it when people will talk, wax lyrical about complex adaptive systems, about attractors, about all of these things, and they'll pull their work. Eventually, they'll pull it back to reductionism. And this is the danger. And this is why I had this quite provocative title, that there's no such thing as a complex adaptive system. Obviously, I'm not actually saying that complexity doesn't exist, or that the complexity sciences aren't incredibly useful and incredibly important. But I'm saying that the tendency to believe in universals is dangerous for us. And so the conclusions of this entire talk, and then we can open up for questions. As a software architect, you will already have a philosophy. You don't know what it is because no one's ever taught you how to express it. Unless you've taken it up as a hobby, it won't be part of your education. It's encapsulated in gut feeling, reflective practice, and it's surrounded by marketing, swirl, random stuff, moonshots. Learning how to use philosophy to question what you believe, what you think as an architect, is incredibly important. And learning how to express it, and then linking it back to empirical experience, empirical practice, is incredibly important as well. And so for architects, the challenge that my book is asking them to take is to ask themselves, are you suffering from the architect's paradox? To be responsible in that case for your own philosophy of architecture. Don't allow your career to be based on a bunch of ideas that have turned up in your head from where you don't know, that are just basically floating around in the ether of our industry, and have demonstrably contributed to the software crisis. For software engineers, this means exposing yourself to thinking outside of STEM. It's not always the easiest thing in the world to do. There's a potential gold mine of new ideas and theories in the heads of good architects. Most good architects pick up heuristics, learn how to deliver these things, but it becomes a set of heuristics, and we need to know what those are, where they come from. And at the end of the day, know thyself, from Socrates, is still the principal piece of advice that you would give. And so if you control the model, it doesn't control you. And the final thing, because one of the cheeky questions I get from belligerent software engineers who sat through an hour of philosophy, is, what am I meant to do with this? What can I build with this? Do you have a library I can download to do this for me? Really what I'm asking them is to understand their own thought processes. And that's a formidable skill in today's software industry. Be able to answer the question, why 3 components, not 2, not 4? Our industry is very young, and we don't know who we are yet. And so moving forward requires a level of reflection and a question of assumptions that we don't always indulge in. And raising our game in terms of our understanding our own philosophies, where they've come from, will help us to do this. And it's not going to be for everyone. For those who are very bought into the idea of correctness, logic, and linear thinking, this is a step too far for them, and that's understandable, and they can carry on building their code. And at the end of the day, what I'm saying to them is that there is no spoon. It's another Matrix reference, which is kind of scary because there's an awful lot of people in my audiences these days who weren't born when that film was released. But it's not the spoon that bends, it's only yourself. These are my contact details and the 2 books. This book here residues, much more technical, tells you how to actually build architecture in uncertain environments. This one's much more focused on what we talked about tonight, goes a lot deeper through the history of Western philosophy, showing this movement from stillness to crisis to movement, and how that's reflected in software engineering. And with that, Barbara, Jocko, we can open up to questions. Oh, there's a lot going on in the chat.
So much going on in the chat. I don't see a lot of questions per se. So first I'm going to ask if anyone has a question about anything that Barry has talked about before I throw it open to some of the comments in the chat. Any software architects out there that want to ask Barry a how-to? No? Okay. All right, so now I'd like to hear from some of you in the chat who had so many things to say. Now, Barry, I just want to clarify before we go any further. This talk is specifically about software architecture and the discipline of software engineering. You're not making any broader claims necessarily for complex adaptive systems or complexity, yes?
I'm not. No, I have a policy of staying in my lane. So I'm only talking about software engineering because it's that's where I've empirically shown that my ideas hold. People love to take these ideas and apply them to lots of other things, which is probably going to happen in these questions now. And I usually say, well, knock yourself out, but it's not empirically verified, it's not empirically supported, so it's not. It's really interesting, and people tend to say, well, one of the questions I get a lot is, can we design organizations using these ideas? And I say, well, if you tell the story, it sounds coherent, but I have not done any empirical work to back that up. And some of the assumptions that you can make with software, because it's nice and rigid, stupid, you can't make about organizations because they're anything but. So yes, this is almost entirely in the sense of software engineering.
Okay, good. I just wanted to clarify that because, sometimes, it's very easy to run this off into other parts of the discipline. And I just wanted to make sure that we were talking specifically in your talk about software. Now we can blow it out from there if you like, or if anybody in the chat would like to. So, does anybody have anything they'd like to share with Barry? I see a lot of Davids in the chat.
More than one, Dave. The question of clarification, right?
Okay.
So if we're saying this purely applies to software engineers, yeah, and we're saying the problem with complexity science is that software engineers will inevitably move it into something reductionist. And therefore the solution is to say there is no such thing as complexity, there are only attractors. Is that's what actually being said? Because that seems to be an argument because software engineers have a very poor and limited education, that the rest of us should abandon our education in favor of their limitations.
Well, yeah. So what I'm saying is that, and this applies, I believe, to anyone, regardless of what they're working with, that and you're agreeing with me in the chat, the complexity of the anthill is not the complexity of the organization. Complexity is not a universal. It is not the thing that we call complexity. In different places is not exactly the same.
Yeah, but I think the trouble is, I think you're getting caught up in a Platonic concept of universals and essences and stuff like that. Complex adaptive systems manifest in different ways. So an attractor is a manifestation; it's an emergent property of a complex adaptive system. But the nature and structure of a complex adaptive system is in common over its manifestations.
Okay, yeah, and that's where we're in disagreement then, because the nature and the structure of an anthill, you're saying that that's the same as the nature and structure of an organization.
Absolutely not.
Okay.
Absolutely not, but there are aspects of the anthill in terms of interactions. The difference in a human system is you have ants, not individual ants. and you have intelligence and you have intentionality. So the system becomes more complex, but that's a fractal relationship with the anthill. Right? It doesn't mean that you can then say that an attractor, which is a phenomenon of complexity in both anthills and in humans, is the defining entity. I mean, you're effectively I mean, I don't buy essences. And by the way, Aristotle came a long way before Kierkegaard. So I don't buy essences, but you're basically arguing that the shadows on the wall of the cave have more reality than the stuff behind the fire.
Well, that's a lot of references.
No, that's what you gave, Barry. Come on. Yeah.
The attractors. So the question is, I have a complex system in front of me. How should I attempt to deal with it? We're trying to teach software engineers how to do this. The first lesson is that complexity is not a universal. So the last complex system that you worked with is different than this complex system, and the tools and techniques that you worked with and used there are not necessarily going to hold in this system just because they're both complex. We're agreed on that, right?
No, we're not actually.
No? Okay.
The first essence is to say, what are the actants? What are the interactions? How did they manifest in our last system? They won't manifest the same way in the next system, but there will be actants and there will be interactions, and there will be repeating patterns. That comes into assembly theory, which we can place some reliance on. So the fact that the emergent properties will be different each time doesn't mean that the nature of what interacts or the nature of those interactions and the nature of the actants aren't actually common across both systems. And that gives us a different way of working on it. And that, by the way, is not reductionist. To break things down is not reductionist. What is reductionist is to assume that the whole can be deprived from an understanding of the parts.
Okay, so you're saying that what works in one complex system can be lifted over to another complex system. So the Spotify model should work from one complex system to another.
No, sorry, I'll say it once more, then I may give up, all right?
Yeah.
What I'm saying is, in common, there are actants, there are interactions. There are constraints, there are constructors. There are ways in which the system actually can be understood. Now, the way those will interact and the phenomena which arise will be different in each case. Right? I don't have to say that, I think you're getting this wrong because you're always looking at the outcome. You're not looking at the starting conditions.
Okay. So you're saying that that actant is a universal, that there's always an actant in the system.
There will always be actants, all right, and they will differ in each occasion. In a human system, they're more complex because they tend to be identities rather than individual ants. So you get more levels of sophistication, but the basic structure is the same. What you then got is different emergent phenomena. And what we need to do, to be honest, I think in software architects, is get them to think in terms of scaffolding, actants, and interactions, and not think about the end purpose of the system.
Okay. Well, I think that I disagree with the idea that structure is always the same. And that's part of what I'm calling logical structuralism. The idea that if we get to the structure and we understand the structure and we understand the interactions of a system, then we understand the future of that system. We fall into this.
Barry, I haven't said that. I've absolutely explicitly not said that.
Okay, but you've said that they're the same. You've said that they're the same thing.
The phenomena will change each time. The outcome will change each time, but you can still understand the actants, the interactions, their limitations, their constraints, and that's a useful process. You can monitor for emergence. To say that there are common elements is not to say that there are common outcomes.
Okay, but I haven't said that either. So I don't
somebody else at this point.
Hmm?
I'll hand over to somebody else at this point.
Okay.
Maybe can I ask, because I think I have a bit of follow-up question.
Okay.
I asked it in the chat.
Okay, one second before we start. Barry, can you stop sharing your screen? Because I can't really see who has their hand up because your screen has sort of taken over my screen.
How do I
You can't click on meeting, Barbara. If you click on meeting, it takes the screen away.
Okay. Okay, so anyway, all right, who asked if they could follow up?
It was me,
Okay.
Mary. Yes.
Okay,
So
and then we'll go
this-
to Erik. Okay, go ahead.
So yeah, my question was similar, maybe a bit more easy terms. What do you see as the real risk if we treat complex adaptive system in the universal terms? Because for me, understanding complex adaptive systems anyway forces us to understand the context, act locally, experiment, and so on. So I wonder, what is the risk in treating it this way?
Yeah, so the risk that I see is that we start to believe that all complex systems, that complexity is a universal thing. That complexity will be experienced in exactly the same way, from complex system to complex system to complex system. And so the danger in that kind of thinking is that we very, very easily, and this happens a lot, fall into the trap of treating the anthill like the social system, like the business system, like the software system. And whenever we see complexity as this thing that's always there every time there's interactions, and rather than just being a word that we're putting on to an experience, that there's an actual thing called complexity that exists in the anthill, that exists in the organization, then we tend to start reducing that complexity, and we start to think that we can use the lessons from one system in another. And this is part of the default philosophy that I'm trying to get rid of in software architecture, which I call logical structuralism. It's this idea that once we've understood the structure, once we've understood the interactions, once we've done that in an anthill, we're qualified to do that in an organization, and we can bring lessons from the anthill to the organization. And those kind of intellectual shortcuts, they're a product of this default philosophy. And that is the danger that I'm trying to keep us out of. I'm trying to move software architects out of the idea that the complex system that I engaged with 10 years ago, which was a business, had a structure, a set of structures, a set of things called processes and capabilities. And those structures I could take with me to the next customer, to the next project, to the next customer, to the next project. That kind of thinking, logical structuralism, leads to the framework. And frameworks have been an incredible disaster for software architecture over the past 20 or 30 years, because they simply do not hold from context to context. And so what I want architects to do is to engage with every context that they engage with afresh, and to think about, not to seek structure, not to seek pattern, not to seek the thing that was there before, but to actually walk around the problem from a number of different perspectives until they actually have a decent understanding of it, instead of constantly seeking these frameworks and shortcuts which have absolutely hammered the credibility of software architecture in the past few decades. And so the risk is that complex adaptive systems, as a complexity science, as a discipline, brings an enormous amount of incredibly useful ideas to software engineering. But if we describe them in that there's this thing called a complex adaptive system, it has interactions, it has actants, it has a structure, and you learn this and you lift that from system to system to system. When you tell that to software engineers who have already been indoctrinated into this logical structuralism, then the path that they will follow is fairly obvious, and it will fall back into that disrepair, the same way that Ralph Stacey talks about how the ideas of systems thinking become absorbed into the dominant discourse of management. And so you start off with all these nice ideas, these words, these things that can help, and you end up right back where you started, which incidentally is exactly where the agile movement finds itself today. For some reason, people are very shocked that we've ended up back where we started. And it's because of this belief that there is some kind of repeatable structure in every single complex system that can be lifted and placed into another system over and over and over again. Careful walking around a problem, understanding that we cannot map everything, that we aren't in control of the complexity that's there, that our addiction to structure, which is especially prevalent in the software industry, is the thing that's going to get in the way of us understanding the systems that we work with. These are the kind of things that I'm warning against. And then I'm not relating this to outcome at all. I'm relating this to how we investigate and understand complex systems. And you won't do that by believing that complexity is an essence or a universal. The very definition of complexity should lead us to understand that it's different every single time.
Okay. All right. So, Erik, you had your hand up.
Thank you, Barbara, and thank you, Barry, for an inspiring talk. This is a wake-up call for the software engineering community, big time. So thank you for that. So I'm not an architect. I'm a hacker, and I'm also a systems engineer, whatever that means, and I'm trained physicist. So having said that, I was fortunate enough to work with a trio of gentlemen who. When taking this back to software engineering, right? So they were not trained developers, they were not trained programmers. One was a rocket scientist, one was a telecom engineer, and the third one was a physicist. So they did attack their challenge or their need in a very, very different way. I mean, they were doing a very complicated software system for telecom switches, and their fundamental starting point was things will go wrong. Things will change. I mean, all the things you talk about, process philosophy, Whitehead, those kind of things. They were not philosophers, but they were sort of practitioners, and they were trying to meet this challenge. So they started from another premise. You know, things will go wrong in the real world. How do we handle that? Hardware will break. There will be software bugs. How do we handle this? And they came up with something fundamentally different to what most software architects and coders and hackers would do. But I think this philosophy that ended up with let it crash because we will let it recover. So that's another way of going about things. And I think it totally resonates with everything you're saying. They were not coming from the traditional math, logic, computer science background. So they therefore saw the world and they walked the world because they were sort of chugging on this problem or need for 10, 15 years in a lab, and they were iterating, they were working with real customers and getting real feedback, but their starting point was fundamentally different. And yeah, I just wanted to share this story. I don't know where I'm going with this, but I was inspired by it, and I thought, you know, there are examples of people doing things differently. I think that's what I'm trying to say, even in the software community. So end of ramble.
So one of the best and loveliest pieces of feedback I get over and over and over again over the last few years is from software architects who, when I explain what it is that I'm doing, why we need to think this way, why we do this way, the feedback I'll get from very senior engineers is that, yes, this is what we do. And what they'll say to me, and what a lot of them have said to me, and these are people who build very big stuff internally at Microsoft, who will say that this is what we do. This is what we do what you say we're doing, but we don't have these fancy words to describe it. We have no way to talk to each other about what it is that we do. But this is how we think. This is how we execute. This is how we think about things. And that's always the best feedback to hear. It's like, so for those senior architects who can already build in complex contexts, and I had to go through that journey too, where you're suddenly able to build big stuff in complex, constantly moving environments, the problem becomes, how did I do that? And when you're asked that question, you don't actually know. And so the last 10 years have been me digging back through the complexity sciences, through philosophy, through computer science, to understand, why do we do the things we do? Why do I do the things I do? Until I reach a point where other architects say, yes, this makes perfect sense. This is what happens in our heads. And that's like a verification that I've hit something here, that we actually have something concrete.
Thank you.
Thank you, Erik. Tiani, you had your hand up.
Yeah, I had a couple of things. One was you mentioned that the how people and I actually hear this almost weekly in my works. I work in a software team and a backend team. They use the word complex a lot, talking about the code, which is like, it can be mapped, like you said, it's mechanistic.
Yeah.
But then you made the point that if you put that a software team or a software engineer into a new code base, a new environment, maybe a new something like that, then they experience complexity. Could you just expand on that idea a little bit more, like where you know, a little bit more around that?
Absolutely. So I describe software engineering as the art, the job of designing a software system as hyperliminal. That's a different kind of liminality than Kevin uses. And what that means is that a software architect has two jobs. One is to define the structure of code, the structure of a software system, which is mechanistic, it's deterministic, and it's that's what we're taught to do at school. And that bit is easy, or it should be easy. If you find that bit easy, then you're ready for a career as an architect. And then the next step is to understand the sort of the complex context that you've got to make that software work in. And that we're not trained for. There might be some hints and rumors that it's wild out there, but what happens is you come out of university, you've been taught logic, you've been taught mathematics, you've been taught that there's this thing called a requirement, which is going to get you into all sorts of trouble. And then you go into a complex environment, a business, you map it out, you get an understanding of it, you take very, very many walks around it, and at the end you have a result, a software structure that works for this context. The danger is that if you believe, hey, I've solved complexity, because complexity is universal, it's going to be the same at the next organization, that leads automatically to thinking that I can take this structure, this set of practices, the way that I've worked here, and I can lift them directly over to the next complex context that I'm going to work with, and then it crashes and burns. And this is a lesson that the industry cannot learn, because if we look at the Spotify model, that's exactly what that is. Is here we have a complex context, which is Spotify and their market and their customers and their culture and their industry and the regulatory pressures they face and all of that. And they come up with a set of ideas that work temporarily for them. And then someone else says, hey, I also work in a complex context, a complex business context. Therefore, your set of ideas should work because we're both experiencing the same thing. We're both experiencing complexity. It's the same thing. So let's take this Spotify model and we'll plug it into this organization. It will definitely work. And every framework, every bit of snake oil that we've experienced over the last 20 years is feeding off this same instinct towards essence that runs through the industry. We constantly look for essence instead of difference. And we look for the structural similarities in things. And that way of thinking leads us into the same traps over and over and over again. And so what I'm trying to teach those architects to do is, okay, it's brilliant that you worked in this complex environment, that you solve the problems, that you have a set of structures. We never want you to forget that set of structures. We never want you to forget the journey that you went on to get to them. But the next time you enter a complex context, forget them. Don't start from that point. Start to look for difference, not for similarity. And it's the same thing if you're analyzing the anthill and the human organization. Look for difference, not for similarity, because you get trapped in this pseudoscientific structuralism where you're saying that if I understand the structures, then I will have some degree of control over this thing. And I think that that tendency turns up again and again and again in the software industry to the point where it's extremely damaging for us. And to the point where it makes it almost impossible to teach architects. And so when I teach architects, which is the bulk of my job, what I have to do is kind of deprogram them and say, look, this belief you have in this logical structuralism that you can carry from system to system to system, it needs to go away, and you need to learn how to navigate those systems through difference, through repetition, not through the carrying of patterns or the identification of patterns or believing that there's a universal complexity that applies everywhere that you meet it.
So just on the identification of patterns, can't those be unique to that context if you were attempting to identify patterns rather than pulling from another space?
So I didn't quite grasp that.
Because you said avoiding identification of patterns, and yet there may be patterns in a specific context that could be useful to understand.
Absolutely. But the way that I prefer that to happen, and so patterns are a big deal in software because we see the same patterns turn up again and again and again in our software in different contexts. And the way that I teach this to architects is to allow your patterns to emerge and then say, oh, hey, that's the same pattern I saw before, not to go into a complex context and say, I'm going to throw this pattern at it and see what happens, because that causes architectural failure very, very quickly.
Right.
And so I see patterns also as an attractor. It's something that emerges in a complex system. And so there's not. And so I'm not saying that there is no such thing as a complex system. Every time we go into a business context, it is a complex system. But that doesn't mean that it has universal properties of complexity or adaptability that it shares across different contexts.
Okay. And then the second thing is and this applies a little bit to the problem solving element versus the how you arrange things, kind of like the deployment of your strategy, or how you arrange things to build together. But it was a few years ago I heard Mary Poppendike give a talk about the difference between being a coder and an engineer. And when she talked about engineering, and how she learned and became a software engineer, it was through collaboration with many different disciplines and lots of going and seeing who they were building this thing for, studying human factors, like all kinds of things I would think that went beyond, kind of like what you said, going beyond what's just in the box of software development or in the box of mathematics and coding, and going out and understanding other things. So she said that putting a lot of different things together has actually allowed you to become an engineer, which is like in her, I think the way she said it was like in terms of being a problem solver. So I don't know if that kind of hits a little bit on what you're saying too.
Yeah, that's very much what I'm saying. And there's a step up from being a programmer to what I call an architect. Some people use engineer to mean programmer, some people use engineer to mean architect, but there's definitely a step up when you realize that the most important thing that you have to deliver, or the most difficult thing to deliver in software, is not code that runs. It's code that runs in a context, and through the attractors, the potential attractors of that context. That's whenever you've actually delivered something. And the first instinct of the coder is to look to structure. And that's what I'm trying to push back on. I think that's what Dave is saying that I shouldn't be pushing back on. But the instinct to seek structure in terms of relationships and interactions, which I would call that instinct structuralism. I've talked to Dave about this before. That tendency to look for structuralism is dangerous to the software architect. It will get you hurt.
Great, thanks.
Peter, you have your...
Peter, yeah.
Yeah, hi all. So I posted a question in the chat, and I think I had this is like a two-sided question, I guess. So the first question is sort of like, why even care about talking about something like software architecture in the first place? Like, it seems pointless. Some people called architects are not doing what they're saying they're doing anyways, and why don't just keep calm, carry on?
Okay, that's brilliant. So what is the point in architecture? What's your role, Peter?
Different role and different context, but I like to talk about design and architecture and test strategy and service design and UX design, and my public role, I guess, is product owner.
Okay, so this question that you're asking has come up a great deal in the last 15 years, and deservedly so. What is the point in architects? Why do we even need them? They don't actually do anything. They draw lines and boxes. They They call us to meetings. They try to gain control over things. That's a very common attitude. And this is your question is a reflection of why I'm saying that software software architecture as a profession has failed to deliver what it said it was going to deliver. And the answer to that is, so if you take away all of those architects who aren't doing their job properly, take away architecture from a software team, you will end up in a horrific mess very, very quickly, unless you're lucky enough to have someone in that team, have at least one person in that team who's already thinking like a software architect. The job of architecture has to be done. The job of making sure that the structure of the application is appropriate for the complex context in which it's going to live, which means that it's going to be able to survive. It's going to be critical as that system moves from a tractor to a tractor. That has to be done. If you take away that capacity from a team, the project will fail. And if you don't have that capacity, then the project will fail. And what you need is someone who has those skills. Now, I choose to call the difference between a programmer and someone who has those skills, I call that architecture. At some companies that I'm working with, that is no longer called architecture, it's called staff engineer. Or distinguished engineer, something like that. But the ability to relate code structure to context is not something that every programmer can do. It's a very small number of programmers who can do it, and it has to be present in a project. I don't really care if it's called architecture or if it's called staff engineer or whatever it's called, but it's absolutely necessary. If you just stay in the little box and write the code without that ability to relate it to context, then you're going to have architectural issues.
Yeah. So okay. So on the flip side, and the other question I had is like, we have done all these things so far, and it's taken us quite a bit. We have a lot of large systems that works pretty fine. We use software all the time, all day, everybody, and it's taken us this far. So some value it has proven to have, whatever we have done. We have a lot of like thousands of open source libraries that are small enough and stable enough over time so we can build other things upon it. And those kind of structures and patterns seems to be useful to creating new things and adding value for customers, for society, whatever. So talking about structure code and finding patterns, how you can do that it's more about finding the granularity and what parts are mostly stable over time, and finding what are those patterns for those finding that type of granularities. That seems to be important in any context.
So there's an awful lot of software out there, and it works. And if you talk to the designers of that software, the people who created the structure, you'll find that what they indulged in as they took that design from nothing to something that works and runs today, is that they will have indulged in a large amount of architectural walking, which this Deleuzian walking that I've talked about. They'll have walked around the problem very many times. And if you show them these ideas, they'll say, yes, this is what we do. This is how we've arrived at the structure of the software. If you can take a pattern, deploy it, and it works, you're not working with a complex context, because, or you've been incredibly lucky. Generally, when people take a pattern and deploy it in a complex context, it's going to get beaten up, it's going to get torn to pieces. They'll find out over time that we need to tweak this, change that, move this component, add this. So an alternative way to doing this kind of work is just to take something, throw it into the complex context and wait for feedback, and then build on that. And there are lots of people who interpret agile software development as being that particular way of doing things. I'm not saying that doesn't work. There are very many software applications today. If you look at Exchange server, email servers, HR systems, accounting systems, that do not work that do not exist in complex contexts. They're bounded. They do a very simple thing that is complicated, not complex, and they can be delivered by pattern. And those kind of projects do not need an architect. They're too simple. An architect, by my definition, is someone who can relate the software structure to the complex context. Does that make sense?
You okay, Peter?
I think I broke him.
You broke Peter?
Trying to find the mute button. It's
Oh, okay.
gone abroad. Well, I had to think about that answer before I feel comfortable saying I'm satisfied. But thanks for now.
Okay, great. Jocko, do you want to
carry on?
Okay, thank you. Jocko, do you want to just ask Barry your question?
Yeah,
About-
caught me off guard.
Okay, there he is. Ha ha.
Not sure my camera will come on. You seem to be using structure in different ways at different places in different contexts at different times. That is causing me to have problems figuring out whether you're saying it's a good thing or a bad thing, or that it's contextual or exactly what it is as we jump around. So, and it seems to be coming up in the comments quite a bit. What do you mean by structure? Or is that really something that you really even want to answer at this point?
So, structure, a definition of structure. Structure is a set of things with relationships between them, which is, yeah, that's all it is. Structure is a set of stuff, a bunch of stuff with relationships between the stuff. Software is pure structure. Okay? There's nothing else there. Software is just structure, and when you're working with software, structure is incredibly important. When you're working with complex systems, structure is fleeting. It's moving, it's changing, it can't be relied upon. It's also almost impossible to completely grasp because there's so many parts and so much stuff is moving. And so if you take the structural thinking of a software architect, you're looking at a software diagram, and that structure is solid. It's always there. It's static. It won't move unless you change the code. And you take that attitude of structure and apply it to a complex context and assume that there is some static structure in here that makes this system the system, then you will find, get yourself into an awful lot of trouble, because that structure, just like the river of Heraclitus, is moving. It's always moving, always flowing. And so structure is fleeting. And so when you engage with a complex system and you think you see a pattern, the structures that make that pattern appear can move, can shift, can change, and they're always temporary.
Well, it's a common problem we have here when we're discussing complexity is different people use terms in different ways. Different groups do at different times, depending on where they are. And I think that's what's happening with the word structure here. It's also because one way to think about it is not whether you have structure or you don't have structure, is by what degrees you have structure and how those structures are changing over time. And I think what you're saying is that certain software developers, let's say, or architects are looking at structure in a static way, whereas the complex system or that what they're interacting with outside of that is maybe not as doesn't have the same permanence or is viewed the same way. So now we have the word structure being used differently by different people at different times to mean different things. So that's the nature of my question.
Yeah, well, so I would say that if you're working with complex systems and you're working with words, then those words are going to mean different things at different times to different people, and that's very much in part of the nature of our work. Derrida was onto this a very long time ago, and with the concept of difference, and that meaning is always just out of reach and always changing and always moving, and I think
so we have to be specific about what structure we're railing against and why we're railing against it, or what structure that we want or we're advocating for, and be very clear when we say that when we're talking about the structure. Am I right? Or
I would say that we should be free to talk about structure and to allow it to have different meanings. So I can say that structure has a different meaning in a software application. Structure in a complex system is an entirely different conversation. I just saw a message pop up from Dave that said that that complex systems have structure.
They do, or they couldn't be a system.
So you're using the word system. You see where we're going to end up.
Loosely, yes, complex adaptive system.
Yeah. So what's a system? It's a bunch of stuff connected to other stuff. So structure is something that is very important to be aware of when it actually exists, when it's static, when there is a structure that persists that endures over a longer period of time. When that structure is fleeting, then trying to grasp that with the same tools, it becomes very, very dangerous. And so it's two very, very different things. The fact is that we're talking about structure, but the English language maybe doesn't have enough nuance to talk about the fact that these are two very different things. The structure of an organization or a set of human relationships is not the same as the structure of a software system.
Well, there isn't a singular structure in any of them. There are multiple structures interacting that emerge into larger scale structures that are fleeting and changing over time. So the structure, trying to nail that down is a conversation in and of itself. But okay, I just wanted to bring that up because it seemed to be a thing in the chat. So thank you.
Okay. Well, we're at the hour. And before we wrap it up, I just want to say that I've been paying attention. I know most of you think I don't, but I do. I pay attention. And there's a couple of words based on what's in the chat and what I've been hearing is there's a couple of terms that I've been thinking about, which is repeatability, which is part of the issue, right? When you're in a fast-paced environment, you're often looking for things that are repeatable. And the problem that Barry, you seem to be talking about is when you're dealing with complex adaptive systems, trying to wholesale repeat things is where you're going to run into trouble. It's not that you're saying there aren't parts that will repeat. And the other word that always came to mind while you and Dave were having your exchange is the word always. It's that these things, you can't always do that. And again, when we're talking about operating in a modern business context, we're often looking for reduction and repeatability. How can I reduce this to repeatable components that I can keep using over and over and over again? And I think that the issue that you have managed to address in this talk is this notion that we have, yes, David Crow, I'm sorry you have to go because I know Barry destroyed your dissertation.
Oops.
In
a good way.
Okay, good. Okay, in a good way. Yay. Is this notion that in our quest to find, small repeatable constituent parts and use them over and over and over again, we're losing our ability or never had the ability to view complex adaptive systems correctly within software architecture. Is that a fair assessment of what you've said?
It could be. Yeah.
For a layman, I am neither. I am neither a complexity science nor a software architect.
So what I would say is this. I would start from the perspective of a flawed research project, but it's all we've got, called the Standish Chaos Report. And the Standish Chaos Report shows us that for software systems that are considered large and complex, which is an arbitrary word, it just means big in their case, large and complex, 94% of those systems will not be delivered in a satisfactory way. And I think that as software architects, we have to figure out how to do our job before we make it repeatable. And now modern business practices and MBAs and all this framework thinking will tell us that no, you have to get to repeatability. Somehow we have to get this thing where we design a software system to work within the confines of a factory model where we can just churn this stuff out. And I'm saying let's build the thing, be able to do the thing before we automate it, make it repeatable. Let's be able to do that. As an industry, we don't know how to do that yet. We have individuals who can do it. And that's what I'm trying to do. I'm trying to figure out what are these individuals doing, including myself, because I don't always know what I'm doing. What is it that we do that produces something that makes it work? What is software architecture? And to answer that question, we have to go down a few levels and understand the philosophical underpinnings. Why do we think like this? Why do we keep making the same mistakes? The very root of those mistakes is structuralism. And I would describe myself, I think the difference that we're seeing between me and a lot of people on this call is a belief in structure in complex systems, and I would consider myself an anti-structuralist who, along the lines of Nietzsche, Deleuze, Bergson, who don't believe in structural analysis of complex systems, and that's where we see the world differently.
Okay, Dave Snowden has accused me of woman-splaining you. So I'm sorry if that's how it came across. I'm just trying to figure out if what I thought I heard is what I actually heard. So on that note, we're at the top of the hour. Are there any final questions or comments? Okay.
Okay, so as one, if I well, you have my email address, everyone. If you have questions or any follow-up or anything you want to discuss.
And how can they find the book? Is the book on Amazon, or where do we find you?
The book is on LeanPub. Let me share my screen just briefly. Let's see what happens.
Yeah, we will add this all to the description in the video.
Oh yeah, okay.
So all of this will be linked to
Okay,
in the
great.
video description.
Those two QR codes will take you to either of the books. And there's my email address and LinkedIn if anyone wants to reach out and ask any questions.
Okay. Tiani, take us home.
I'll take you. Thank you so much for coming today, Barry. And I have to go back and watch a few more times. There's some new terminology for me, and I'm sure for everyone else, and really enjoyed the conversation and everyone putting in their thoughts and learning our similarities and differences into how we think about these things. And for everyone, we have another talk coming up in February 18th. Our friend Dave Knoll will be here sharing some of his ideas too. So hope you all have a great rest of the day.
Thank you.
Thanks, Barry. Bye.
Thanks, Barry.
Thank you. Bye.
Thanks, everyone.
Thank you.
Thank you. Take care.
Thank you.
Bye-bye.
Bye-bye.